So today I wanted to give some worked examples of how to deal with inelastic collisions specifically. So as we know, in most collisions, we're going to see that the external force is zero. I'll show you how to check for that. And then if the external force is zero, we know that momentum is conserved. If kinetic energy is also conserved, then we call the collision elastic. And if kinetic energy is not conserved, then we call the collision inelastic. In the case of an inelastic collision, you have to know how much the kinetic energy is not conserved, and I'm going to show you that. And that allows you to solve for one of the knowns and unknowns in this problem. A lot of dealing with conservation of momentum problems is figuring out what is known and what is unknown, going from the conservation laws that you know and working outwards to solve all the variables in the problem. So first I want to explain what I mean by knowns and unknowns. So let's imagine that we have just two generic objects of mass 1 and mass 2 with some momenta p1 and p2 that collide, okay? And this is all we know. So we don't know if the collision is elastic or inelastic. If it's inelastic, we don't know how much energy was converted from kinetic energy to something else. And we don't know anything about the final momenta of these particles. So in this case, we don't actually have enough information to solve the problem. And I'll show you what I mean by that. So we know that the initial total momentum of the system is P1 plus P2. Okay? And this is actually two equations. And we also know the initial kinetic energy and we know that the initial kinetic energy is going to be the sum of the square of the speeds weighted by the masses. Okay? So when I say that this is two equations, what I mean is the initial momentum in x is, and the initial momentum in y okay? So in this particular situation, I have three equations, right? I know the initial kinetic energy, I know the initial momentum in the x direction, and I know the initial momentum in the y direction, right? What I need to find out is the final momentum in the x direction and the final momentum in the y direction, right? And the final kinetic energy. Okay, so my unknowns are the velocity in direction 1, the velocity of object 1 in x, the velocity of object 1 in y, the velocity of object 2 in x, and the velocity of object 2 in y, right? So I have in here three equations, and what I have unknown, right, plus, so unknown is delta E, the change in energy, right, VF, x, 1x, V1, y final, V2, x final, V2, y final. So in this particular case, I have, if I have an inelastic collision, I have essentially I have essentially 3 equations and 5 unknowns, right? So I can't solve this problem. So what I need to do is add more constraints to the problem, or understand more about, let's say, what the final momenta are, and then I can start to solve the problem. So the first example that I want to give you of something like this is something called the ballistic pendulum. So the ballistic pendulum is basically you have some mass which is fired into a block, and the block embeds in the wood and comes to rest. And the question is, what is the speed of the bullet as it entered the block if the block can go up to some height, h? Okay, so how do we solve this problem? So we're going to work backwards. So what we're going to ask is, if the block made it to some height h, what was its initial kinetic energy? If we know its initial kinetic energy, then we can find the speed. Okay? I'm going to show you how to walk through all this. So even though this is a conservation of momentum problem, the first step is a conservation of energy step, because we need to go from the final potential energy, the height, to the initial kinetic energy. Okay? So we're going to say delta K is minus delta U. K final is 0, right? Because the block is at rest. Therefore, K initial is equal to delta U. To write this down a little bit more explicitly, K final minus K initial is equal to minus delta U. So 0 minus K initial is equal to minus delta U. Okay, this is just still conservation of energy. Then the next step is, okay, now we have the initial kinetic energy is equal to delta U. Now we write down the gravitational potential. This is mgh, right? Therefore, and this is 1/2 mv initial squared. Okay, this vi is total. So this is the initial velocity. If I have a block and I have this object embedded in it, it's the initial velocity before the block starts swinging, but it's the final velocity before the bullet is embedded. Okay, so there are 2 steps in this problem, and I'm going backwards in time. That's important. So now we have 1/2 mvi squared equals mgh, right? The masses cancel. The 2 goes over to this side. Vi squared is equal to 2gh. Vi equals 2gh root 2gh. Okay, so this should be familiar to you both from the kinematics section and also from solving from it many times in our conservation of energy section. You can just try to go and plug in this equation, but I always like to do the derivations in these worked examples as far as possible, basically to show you that even if you don't have, you don't need a whole slew of equations memorized for these things. You just need a couple of them and then understand how to work through them to get the ones that you need. So this is the final speed of the total block. Okay? Now, what the question is asking is, what was the speed of the bullet as it entered the block? So in this particular case, right, then what we have is we have some object which has a mass equal to the mass of the bullet plus the mass of the block. And this has some velocity, v initial equals 2gh square root. Okay? So this object has momentum, mvi in the x direction. Okay? So therefore, the mass of the initial momentum of the bullet, because it's the only thing with momentum in the reference frame that we're working in, is going to be the same as the final momentum of the block. So we can write down okay? We know this, right? It's the initial velocity times the total mass of the system. Therefore, the initial momentum of the bullet is just going to be m bullet plus m block, right? Times root 2gh. Okay? What's this? This is the mass of the bullet, and the initial velocity of the bullet is equal to the mass of the bullet plus the mass of the block, root 2gh. So the initial velocity of the bullet is equal to okay, so this is how to deal with what's called a perfectly inelastic collision. A perfectly inelastic collision is one where the two objects stick together. When the two objects stick together, all the momentum is contained in a single object with a single velocity. And that helps you reduce the scope of the problem, right? Because if we go back to what the challenge was, right? The challenge is we have these four unknowns, okay? But in a perfectly inelastic collision, essentially what you have is V1F equals V2F, okay? And because this is a vector quantity in 2 dimensions, you can treat it like two equations. And so you can either think about this as, okay, now I went from basically two equations and two unknowns to, or sorry, let me correct myself. I went from 3 equations and 5 unknowns to 5 equations and 5 unknowns, which is, right, solvable, right? In other words, we don't need conservation of energy because conservation of momentum alone will tell us what's happening. If we know the initial momenta of both particles, we can find the final momenta of a single particle. So I hope that that was helpful in understanding conservation of momentum in perfectly inelastic collisions. You have a homework problem which talks about conservation of momentum in 2 dimensions, dealing with conservation of momentum in perfectly inelastic collisions. I'd like you to note that in this case, right, you know the initial momentum of the system as a vector quantity. And therefore you know the final momentum of the system as a vector quantity, and you know the final mass of the system. Therefore, you can solve for the velocity of the final object, right? In other words, the trick with perfectly inelastic collisions for 2 objects is I know generally P1 initial and P2 initial. Okay, so this has some P1 initial, and this is some P2 initial, right? We know that the final momentum is the sum of the initial momenta. If the object is stuck together, right, there's only one object, essentially, in the final system. Therefore, I only have one quantity to solve for. So if I know the initial momenta of all the particles in my system for a perfectly inelastic collision, I can solve for the final momenta without needing to invoke conservation of energy. Perfectly inelastic collision means the kinetic energy of the final system is minimized. For partially inelastic collisions, right, I generally need more information than that. I'm going to need to know how much energy is lost, or I'm going to need to know the final velocity of one of the two particles. So thank you for watching. I hope going through this worked example of the ballistic pendulum was helpful and how to apply it to your homework problems. I hope you can see the extension from 1 dimension to 2 dimensions. And I'll be coming back with this for more worked examples dealing with angular momentum, dealing with torque, and dealing with partially inelastic collisions. Thank you.